Hello, everyone, and welcome back to Control X Engineering. If you're new here, my name is Akhil, and if you have been following our channel, you know we have already covered IC 61131-3 languages for PLC programming, motion control, and many other topics in getting started with TwinCAT. Today, we are diving into something super practical for industrial automation: serial communication in TwinCAT I using the TF6340 function. Whether you're trying to connect a barcode scanner, a sensor, or even legacy RS-232 devices to your PLC, this tutorial will show you how to make it happen. We'll walk through all these steps, from wiring and configuration to writing the PLC program that sends and receives data over a serial line. By the end of this tutorial, you'll be able to confidently integrate serial devices into your Beckhoff PLC projects. In this tutorial, we'll walk through everything, review the TF6340 function and the serial communications PLC library, show you how to set up an EL6001 terminal for serial communication, configure and instantiate the library function blocks in your PLC project, and send and receive data over serial bus using structured PLC code. By the end of this video, you'll be able to confidently integrate serial devices into your TwinCAT projects. So grab your cup of coffee, fire up TwinCAT, and let's get started. The complete documentation for working with the TF6340 serial communication function can be found at Beckhoff Information System website. Before we dive into the TwinCAT part, let's first review what serial communication actually is. Serial communication refers to sending data one bit at a time over a single communication line. It's a well-established method, particularly useful for point-to-point or multi-drop communication with low-complexity devices. Two common standards dominate the industrial space: RS-232 and RS-485. RS-232 is a single-ended standard between a transmitter and a receiver. Usually the communication is bidirectional, so both devices can transmit and receive data. I mentioned that RS-232 is single-ended. This means that the data is transmitted as a voltage difference between a single signal wire and a common reference point, typically ground. Thus, at a minimum, at least 3 wires are required between the two devices. RS-232 stands for Recommended Standard 232. Is a standard defined by the EIA for serial data communication. It's like a blueprint for a specific type of serial communication. Each end uses one transmit line called TX and one receive line called RX, as well as a signal ground reference line called SG. It uses voltage levels like plus minus 12 volts, which are quite noise tolerant at short distances. However, it's limited to point-to-point connections only and short cable lengths, typically under 15 meters for reliable operation. The transmit line of one device connects to the receive line of the other to facilitate bidirectional serial communication. RS-485, on the other hand, is differential, meaning it transmits data using voltage differences across two wires, A and B. This allows for higher noise immunity, longer cable lengths, typically up to 1.2 kilometers, and higher data rates. RS-485 also supports multi-drop configurations, so multiple devices can be addressed on the same bus. This could be the topic of discussion for another video, so we will leave it at this for now. Imagine we have a sensor that uses a serial interface to communicate its measurement data to the PLC. Suppose it has a measurement value of 89 that needs to be transmitted over its serial interface. This value will be sent by the sensor over the transmit signal wire in binary form using ones and zeros, and ultimately received by the PLC. For transmission, these bits are sent sequentially over the transmit line. Meanwhile, at the PLC side, the data is received sequentially and stored into a receive buffer. We will review the actual mechanism with respect to TwinCAT later in this tutorial. When using serial devices like a sensor, it is important to match the serial communication parameters of the sensor in the PLC. These are the common communication settings that need to be configured on the PLC side. Baud rate is the data transmission speed measured in bits per second. Common baud rates are shown here. Parity is an error checking mechanism used to ensure the data integrity during transmission. It is primarily used to detect single bit errors during transmission. If the parity of the received data does not match the expected parity, it indicates that an error has occurred during transmission. However, parity cannot detect multi-bit errors, nor does it provide any sort of error correction. Common settings are even, odd, or none. For even parity, the parity bit is set such that the total number of ones in the data frame, including the parity bit, is even. For odd parity, the parity bit is set such that the total number of ones in the data frame is odd. Data bus refers to the number of bits used to represent each character of data. Common settings are 7 or 8 bits. The choice depends on the requirement of the devices being used. Stop bits indicate the end of a data packet. Common configurations are 1 or 2 stop bits. The choice of stop bits can affect the timing of data transmission. When interfacing sensors with PLC that uses serial communications, the sensor's datasheet will specify its COM settings. For example, you might see something like this. This means it uses baud rate of 9600 bits per second, 8 data bits, no parity bit, and 1 stop bit. In conclusion, when setting up serial communications, ensure that all parameters are identical on both devices to facilitate successful data transmission. Understanding these settings is crucial for troubleshooting and optimizing communications between the devices. Next, let's take a look at the Beckhoff EtherCAT terminals that support RS-232 serial communications. The EL6001 is the single channel version and allows connection of devices with RS-232 interface. Similarly, the EL6002 is a two channel version and allows connection of devices with two electrically isolated RS-232 interfaces with 9-pin D-sub connector, also known as DB9 connectors. Both these terminals operate in full duplex mode with data transmission speeds up to 115.2 kilobits per second. These terminals have one receive buffer and one transmit buffer per channel. The LEDs indicate the operating state of the terminal and data transmission status as shown in this table. The run LED indicates the status of the state machine of the EtherCAT slave terminal. When the terminal has been correctly configured in TwinCAT and its operation state switches to op state, the run LED turns on solid green. The terminal is now ready to communicate with a serial device. The other LEDs indicate the data transmission status. The EL6001 has two green LEDs, one each for data transmitted and data received. The EL6002 has two channels and uses dual color LEDs, one for each channel. The corresponding LED turns either green to indicate received data or orange for transmitted data. The connection points on the EL6001 are identified as shown. The minimum number of connections for reliable serial communication between the PLC and sensor are the transmit, receive, and ground connections. If using a shielded cable, then the cable shield can be connected to the connection point 4 or 8 at the bottom. If using the two-channel EL6002 terminal, then this image shows the pinout for the DB9 connectors. Here the pins 2 and 3 are the receive and transmit respectively, and pin 5 is the ground connection point. For the purposes of this tutorial, I will be using the EL6001 single-channel RS-232 terminal. Let's look at the I/O node in TwinCAT and see how this terminal is configured. My setup looks something like this. I will be using my CX5140 IPC for the PLC runtime. For the serial communication, I'll be using the EL6001 terminal and terminate the setup with the bus end cover EL9011. Each EtherCAT terminal station must be terminated at the right hand end with an EL9011 to protect the E-bus contacts. After scanning the hardware, we should now see the EL6001 added to our I/O configuration. Let's review the configuration in more detail. Let's look at the COM inputs first. This is the 16-bit status word and is part of the input process image transmitted from the terminal to the serial controller in the PLC. The EL6001 terminal operates in 22-byte mode, which means that 22 data bytes can be transferred to and from the terminal. 3 PLC cycles are required for each data exchange. These 22 bytes will need to be linked to a data structure in the PLC, which we will review shortly. Next, let's look at the COM outputs. Here we'll link the output data types from the PLC to the terminal. The control word is part of the output process image and is transmitted from the serial controller in the PLC to the terminal. These are the 22 output bytes from the PLC to the terminal. These 22 data bytes will need to be linked to the output data structure in the PLC. In order to use the serial communications function in the PLC, we will need to include the TC2 serial COM library from the repository. This library can be found under Communications in the Add Library pop-up dialog box. This library provides function blocks and data structures for communicating with serial devices. Various function blocks for sending, receiving, and configuration are available in this library. All function blocks support multiple instances, so that depending on the processing capacity of the IPC, any number of serial interfaces can be operated in parallel. The use of the serial COM library requires activating the appropriate license from Beckhoff. In this case, we need to activate the TF6340 license, which enables serial communications functions in TwinCAT. For this tutorial, we can use the license using the 7-day trial activation. To use this in your equipment for deployment, please contact Beckhoff Sales for purchasing the full license. The appropriate function executable will also need to be installed on the runtime. In my case, I will need to install the TF6340 executable file on the CX5140 IPC which I'm using. Let's head over to Beckhoff's website and navigate to the TF6340 product page. At the bottom of the page, click on Documentation and Downloads. Under Software and Tools, find the executable file for TF6340 function. We will need to download this setup file and copy it to the Beckhoff IPC where the PLC runtime or XAR lives. You can do this by connecting a keyboard, mouse, and monitor to the IPC. In my case, both my development computer and the Beckhoff IPC are part of a local area network, so I just use remote desktop to remote into the IPC. Once copied, we have to run the setup file as administrator and follow the prompts for the installation. After the installation has completed, click on the Finish button to exit the setup. The TF6340 function has been successfully installed and is now ready for use. The maximum effective data transfer rate depends on the PLC cycle time. As an example, for communication with a serial device at 9600 bits per second, a cycle time of 1 millisecond is required. In many large applications, such a short cycle time for the whole PLC would heavily load the runtime IPC, depending on its performance level. Since for most applications, longer cycle times of 5 or 10 milliseconds are usually adequate, it is possible with the aid of this library to decouple the data traffic between the PLC and the hardware from the rest of the PLC application. We can do this by creating two separate tasks in the system node. The standard task runs the application PLC with the conveniently long PLC cycle time, like 10 milliseconds, for example, while a second task runs with a faster cycle time, like 1 millisecond or shorter. It may need to run even faster if using higher data transfer rates. Data buffers of type COM buffer from the TC2 serial com library are used to decouple the different speeds of the fast communication task and the standard PLC task. They are read and written asynchronously. The function blocks for receiving and sending data, which we will look at shortly, make use of only an additional data buffer for data exchange and are thus independent of the hardware being used. In all cases, a communication block using the serial line control function block from the library is called in the fast task. This function block handles the data traffic between the receive and transmit buffers and the hardware with maximum speed in the background. Let's look at the serial comms library in more detail. As we reviewed, the serial line control function block looks at the communication between the serial interface terminal, EL6001 in our case, and the PLC. This function block is called cyclically using a fast task, and then places the received data into the RX buffer. If there is transmit data available in the TX buffer, then that is sent to the interface at the same time. Because the function operates independently of the application, it is referred to as a background communication and is usually made to operate in a separate fast task, as we learned earlier. There are several function blocks available to handle the send and receive operations. The background task puts the received data in the receive buffer, and we can use one of the receive function blocks to retrieve that data for use in our PLC application. For example, we can use the receive byte function block to receive a single character from the receive buffer. Alternatively, the function block receive a string can receive a string of characters from the interface and store it in a variable. However, for our application, I'll be using the receive data function block, which is much more versatile and can retrieve data of any type from the interface, storing it in the receive data variable. The start and end of the data stream are recognized by various mechanisms, which can be combined with one another. It comes with several optional inputs. For example, if a variable is passed to the prefix input, then the first character of the received data must be the same as this prefix. Other characters are discarded. If no prefix is applied, then the received data starts with the first received character. Similarly, if the suffix input variable is applied, then the input data is read until the end of the received data reaches the suffix. The output boolean data received becomes true for one PLC cycle only to indicate that the received data is ready in the received data variable. The number of characters received is given in len received data. There are several function blocks available for sending data. For example, you can use the send byte to send a single byte to the interface, or use send string to send a string up to 80 characters. For longer strings, there is send string 255, which can be used to send strings with length of 255 characters. However, we will be using send data, which can be used to send the contents of a variable of any type to the interface. To use this function block, we need to point to the variable using a pointer and specifying the length of the data to be sent. The busy output stays high as long as transmission is active. When the data has been successfully sent, the busy output bit goes false. Now that we have covered the serial send and receive function blocks, let's look at the serial device that we will be using in our application programming for this tutorial. Our serial device in this case is the AR100, which is a compact triangulation laser sensor from Acuity. The part number that I have comes with standard RS-232 serial interface. which we will connect to the EL6001 terminal. After reviewing the sensor's documentation, I found that its default baud rate is 9600 bits per second, uses 8 bits of data, 1 stop bit, and even parity. So this is the setting we will need to configure on the Beckhoff side. To talk to this sensor, we will have to send a request from the PLC. In response, the sensor acts upon the request and sends the appropriate reply if applicable. For example, we could ask the sensor to start streaming data, and we could get distance measurements streaming over the serial bus in response to our request. Or we could send a request to turn the laser on or off, in which case the sensor acts upon our request and there is no reply. There are various other request types like setting the baud rate, slave address, sampling period, data averaging, etc. Next, let's review how these requests are sent to the sensor. This table is from the sensor's documentation. As we can see from this table, the request from the PLC contains several bytes, which are identified in this table. The first byte is the device address, or ADR. Its factory default address is 1. But as we can see, the address byte's 7th bit, or the most significant bit, is 0, and the remaining 7 bits are the device address. So effectively, this entire byte will be 1 in hex. The next byte is a bit more interesting. Its 7th bit should be 1, and bits 0 to 3 are the code request bits, identified here as COD. These 4 bytes are optional message bytes and used with certain request types. This section of the sensor documentation shows the request codes. These are the ones I'm interested in and will be the ones we'll implement in our PLC project. Code request 6, which is inquiring of result, requests a single measurement from the sensor, while request 7 requests continuous streaming of measurement data, and code request 8 stops the streaming data. These codes have to be inserted into the lower nibble of the second byte that we send to the sensor, as we saw earlier. So the result of inserting these codes into the lower nibble gives us these values for the 3 requests. Thus, if you wanted to request the sensor to start streaming the data, these are the 2 bytes you would need to send. The first byte is the address, and the second byte is the request code. Turning the laser on or off requires using request code 3, which is writing of parameter and then specifying the 2 message bytes, which are the parameter code and the parameter value. Elsewhere in the documentation, it specifies that the parameter code for controlling the laser on or off requires parameter code of 0 and value of either 0 or 1 to turn the laser off or on, respectively. So we have to use the remaining 4 bytes of the request to send the parameter code and the parameter value. Parameter code is sent as message 0 and parameter value is sent as message 1. Thus, the complete request will require sending these 6 bytes to turn the laser on and these 6 bytes to turn the laser off. Lastly, let's look at the format of the response from the sensor when we request for distance measurement. According to this table from the sensor documentation, the response is 2 message bytes encoded in 4 bytes. Byte 0 contains the lower tetrad of the 0th byte of the message. Byte 1 contains the higher tetrad of the 0th byte of the message, and so on for the first byte of the message. Also note that the most significant bit of each byte is a 1, and the actual message is contained in the lower nibble or bits 0 to 3. For this tutorial, since our focus is on PLC serial communications, I will be ignoring the other bits shown here as CNT and SB bits, which are used for data validation purposes and must be properly integrated in the PLC application for the intended purposes. Once we have retrieved the message bytes and formed the complete message indicating the distance, we have to use this formula to determine the distance in millimeters. Here D comes from the message bytes and R is the range of the selected sensor. For this sensor I'm using, the range is 250 millimeters. Let's try an example to see how this works. Imagine these are the 4 response bytes we received from the sensor. Extracting the lower nibble containing the message from these bytes gives us. Arranging them from the low byte to the high byte gives us a value in hex. Converting to decimal and applying the formula gives us the required distance in millimeters. Now that we know how to send requests and interpret responses from the sensor, let's hop on to TwinCAT and start coding.
Hi, this is Andrew, and today we will be working with serial communications. The serial device is a laser sensor, and I will be showing you how to communicate with it in TwinCAT. Let's start with adding a new TwinCAT project. Okay, The solution has been created. Let's add a new PLC project. I'll select Standard PLC Project and provide a name. PLC project has been added. The first thing to do is to add the Serial Communications library to the project. Under the References section, click on Add Library. Then navigate to the Communications section and Serial subsection and select the Serial Com library. We need to add one more library to the project, since we will be making use of some special functions from TwinCAT's Utilities library. In the search bar, type tc2_utilities. All required libraries are now added. Next step is to create a global variable list. So, right-click on GVLs and add a new list and call it GVL_serial. Okay, I'll create the necessary variables we're going to need. First, I'll create input and output variables from the Serial Comms library. These will be linked to the corresponding PDOs of the EL6001 terminator. Next, I will need receive and transmit variables of type COM buffer to hold the data for use with the send and receive function blocks. And finally, I will create two more variables to map to the I/O terminal for diagnostics purposes only. These two variables are optional and not required for serial communications. For the next step, we have to create the serial line control program, which will make use of the variables we just created. Start by adding a new POU of type program. As Akil explained, the serial line control program has to run in a fast PLC task, so we will call this fast serial comms. Here we will need to instantiate the serial line control function block from the library. I'll call it my serial line control. I'm also creating a variable to hold the error ID for diagnostics purposes. We can use the input assistant to add the instance. For the mode, there are several types defined in the library. For our terminal, I am using the standard 22-byte mode. Next, the COM in and out inputs use pointers, so I will be pointing to the corresponding variables we created in the GVL using the address operator ADR. Next, we have to specify the size of the input process image of the serial hardware being used. The size is determined and assigned using the sizeOff function and specifying the input COM variable. The error ID output provides an error code when an error occurs. Link this with the error variable we created. Finally, link the transmit and receive buffers. We will use these in our function blocks later to read and write to the laser sensor. And this program is now done. We can save and close. Before I forget, let's head over to the System node and create a special fast task to run this POU. Under Tasks, add a new item and select TwinCAT Task. Change its name to Fast. Open the Real-Time Settings page and update the number of cores. I will assign the isolated core to the runtime. Also change the base time to 100 microseconds. Don't forget to hit the Set to Target button to update settings on the target. Mine's already set, so I will cancel. We're done here. Close this window and head back to the two tasks to update their cycle times. For the main PLC task, we want to set the cycle time to 500 microseconds, so select 5 cycle ticks. And for the fast task, select 1 cycle tick, which will make this task run at 100 microseconds. Meanwhile, back to our PLC project, add a reference task, and select the fast task from the list of available tasks, and click Open. The fast task is now added to our PLC project. The other task is calling the main program. Similarly, we will call the fast serial comms program from the fast task. Right-click to add an existing item, and select the fast serial comms program in the dialog box. Now the fast serial comms program will run at 100 microseconds, while the main program will run at 500 microseconds. Now we can start programming the application logic. Let's head back to the main program and start by creating the required variables and function block instances. First, I am instantiating the send data function block, which is coming from the serial comms library under the send and receive folder. Here is the receive data function block, which I will instantiate shortly. I'll finish off by declaring the data arrays of byte type to send various requests to the sensor. I also need some trigger functions to reset the execute bits on the falling edge of the busy output bit of the send function block. Next, I'm declaring the byte arrays for the laser on and off requests, which if you recall required 6 bytes to be sent to the sensor to turn it on or off. We're done with the send related variables. Next, we need to instantiate the receive data function block and a byte array to hold the 4 receive data bytes. Finally, I will need some more variables to convert the received data to string to store them as hex and to be able to concatenate them, as explained by Akil during his presentation. And lastly, I'll need some Boolean variables to trigger sending the various requests to the sensor. We're done with the variable declarations. Let's save the project and start creating the logic. All the required logic can be added as actions to the main POU. Depending on which of the send bits is set, one of the send request byte arrays will be sent to the sensor. To request a single measurement, we have to send hex value 86 as a byte. So this piece of logic will send the appropriate byte when the execute send 86 bit is set to true. To do this, use the input assistant to add the send data instance we created and pass the appropriate variables to it. At a minimum, we only need to specify the address of send data byte array, its size, and the transmit buffer. Next, I use the falling edge trigger to reset the execute bit for next use. And we're done with this action. Similarly, I will create actions to send values 87 and 88. The next action is to receive the reply from the sensor. So let's add an action to write that logic. Let's call the instance we created for receive data. We don't need to populate all the inputs. I will remove the ones we don't need and only link the necessary ones. This will read the 4 bytes of data from the receive buffer and populate them in my data array. The next action is to interpret and convert the received 4-byte data into distance measurement. The first step is to convert the byte information to hex value and store in an array. I will implement a for loop to convert each byte of received data to hex and store the info as strings. Now I can do some string manipulation to form a new string containing the distance value in hex. In order to use this in the conversion formula, I have to convert the string back to a number and then apply the formula to get the distance in millimeters. And we're done. Close and save. The last action we need to add is to control the laser on and off. This will be similar to the first 3 actions we created to send requests 86, 87, and 88. Here we have to send the request byte array corresponding to laser on or off, depending on which bit is set to true. Similarly, I'll add the logic for laser on. And we're done. Save and close. Now that all our actions have been created, we just need to make calls to them here in the main program, and we're done. And with this, we're done with the PLC part. Now let's configure the I/O node and scan the EL6001 terminal into our configuration. To add a route to the IPC, let's start by choosing the target system and adding a route to it. I know the target's IP address, so I will enter that here. My CX5140 has been discovered, and I already have a route added. If yours isn't, you can hit the Add Route button. I will close this dialog box, select the IPC, and hit OK. We are now connected to the target IPC and can proceed with scanning the I/O terminals. Since the terminals are directly attached to the CX IPC, I will select Device 1, EtherCAT, from the list and uncheck everything else. Alright, the connected terminals have been scanned and add it under device 1. Let's expand the EL6001. We can see its inputs and output PDOs. As Akhil mentioned, we have to link the corresponding variables from our PLC to these inputs and outputs. I'll start with the inputs, linking the status first from my global variable list. For the 22 input bytes, I will select all the PDOs and link them using the multi-link option. They will link to the structure called D from the serial COM library. Similarly, let's link the COM outputs, starting with the control word and the output 22 bytes. I also like to link the WC state bit and EtherCAT state PDO for diagnostics purposes. Next, we have to change the serial communication setting for the terminal to match with the sensor serial settings. Navigate to the COE Online tab and scroll down to parameter 4073 to check the baud rate setting. Make sure this is set to 9600 from the drop-down menu and click OK. Next, we have to change the data frame setting in parameter 4074. The sensor documentation specified a setting of 8E1. We're done with the I/O configuration. Now we can go ahead and activate this configuration. I will go ahead and click OK to switch the PLC to run mode. New configuration has been activated and PLC is running now. Let's log in and test our PLC. I will start with the main program and try turning the laser on and off. I will put my mug in front of the sensor to see the laser beam. OK, setting the bit to true. That's awesome. The laser turns on. We can see the blue laser beam. Let's try turning it off. Nice. We are able to control the laser on and off. This is all great. But let's see if we're getting any measurement data from the sensor. For this, I will add a scope project so we can plot the distance measurement. Right-click on the solution and select Add New Project. Select YT Scope Project and click OK. The measurement project is now added. Right-click on the data pool and select Target Browser. Navigate to the distance variable and add that to the data pool. Now drag the variable to the axis. In Scope Properties, I will increase the line width so it is easier to see on the chart. And we're all set. Let's get the chart recording started. I will open a visualization that I had created for this tutorial to interact with the PLC more intuitively. It's a simple visualization, really. It has buttons for laser on and off, as well as start and stop data streaming. Let's log in and see what we get. I'll turn the laser back on and start streaming. Looks like we're starting to get something. Let's see what happens when I start moving the object in front of the sensor. That's awesome. We're getting live data from the sensor using serial bus communication. That's all there is to using the TF6340 serial communication function and the EL6001 single-channel terminal in TwinCAT. Hope you enjoyed today's tutorial and hope to see you in the next one.
That's all for today's video. If you have any questions or suggestions about today's video, please leave them in the comments below. If you found this video helpful, then please consider subscribing so you don't miss out on future tutorials. As always, thank you for watching and keep innovating.